Okay, hello everyone. Welcome back. This is our last piece of chapter 6 and chapter 11, relating energy, heat flow, and phase changes. And so in this video, we're going to talk about an approximation for the Clausius-Clapeyron equation. And so in the previous video, we talked about how to experimentally use the Clausius-Clapeyron. And that would be having multiple data points. Sometimes when you collect data, you cannot collect a large number of data points. And in this case, when this happens, we can make an assumption that 2 data points is enough. The assumption is that the 2 data points fit the line. This is only a good assumption for the Clausius-Clapeyron relationship if the temperature range measured is reasonably small, so within about 100 Kelvin. So if I have 2 data points, the form of the Clausius-Clapeyron, remember we were talking that it's the multiple data point version, is the natural log of the pressure of vaporization is equal to negative delta H of vaporization over R times 1 over temperature plus the natural log of beta. That's a T. So if we only have 2 points, what we can do is we can plug things in and we can use that. We can subtract these 2 points because really what we're thinking about is the natural log of P vape over 1 over T gives us a line. Well, if we only have 2 data points, we can think about connecting those with a line. And algebraically, the way that this derives out gives us this form of the Clausius-Clapeyron. And so I like to call this the 2-point form. Now, we only use this form when we have 2 points. This form is the mini-point form. They're the same equation. The mini-point form is preferred because we get much better data. We get much better fits of our line if we have lots of data points in here. It helps us with our error, but sometimes we can't get those. Now, when using the 2-point format, it does not matter which pair of data points you define to be P1 and T1 or P2 and T2. So we can have P1, T1 up here and P2, T2 down here. Or these can switch. Both are possible. Both are fine. It does matter that P2 is paired with T2 and P1 is paired with T1. So it matters that you keep the points together, but it doesn't matter which one you number 1 and 2. It also does not matter what units you use for pressure as long as the pressures have the same unit. Now, temperature must be in Kelvin. And this is because there's this R term, the ideal gas constant term, which has units of joules per Kelvin times mole. And so our temperature has to be in Kelvin so that the Kelvin of the ideal gas constant will cancel out. Okay, so let's work an example. Methanol has a normal boiling point of 64.6 degrees Celsius and a heat of vaporization of 35.2 kilojoules per mole. What is the vapor pressure of methanol at 12 degrees Celsius? Okay, so the first thing that we need to figure out in this problem is what it means by a normal boiling point. Well, the normal boiling point is a pressure of 1 atmosphere. And so if we call this P1, our pressure is 1 atmosphere, and our boiling point, our T1 at that pressure is 64.6 degrees Celsius, or if I add 273.15, I get it to be 337.75 Kelvin. And then for our second point, P2 is what we want to find, and T2 is at 12.0. And if I add 273.15 to get it to Kelvin, I get 285.15 Kelvin. So now I'm going to plug in my values and start solving my problem. So P2 is what I'm trying to solve for. P1 is 1 atmosphere equals negative delta H of vaporization. Which is given to me of 35.2 kilojoules per mole over R, 8.314. I'm going to put my R in terms of kilojoules since that's what my enthalpy of vaporization is. Kilojoules per Kelvin times mole times 1 over T2 is 285.15 Kelvin minus 1 over T1 is 337.75 Kelvin. So now we get to start doing algebra. The first thing that I do is I turn the fractions on the right-hand side of the equation into numbers. And so this gives me the ln of P2 over 1 atmosphere is equal to negative 4.23 times 10 to the 3. Nope. Hold on. Okay, so this is negative 4.233 times 10 to the 3, 1 over Kelvin, times 1 divided by 285.15 is 0.00351 1 over Kelvin. I have my units wrong here. This is 1 over Kelvin, which is Kelvin, minus 1 over 337.75 gives me 0.00296 over Kelvin. And so the natural log of P2 over 1 atmosphere is equal to, if I subtract these two numbers and multiply by what's in front, I get a negative 2.33, and this is now unitless. So to get rid of this natural log, I'm going to raise both sides to the e, and so these cancel, and so I get P2 over 1 atmosphere is equal to e raised to the negative 2.33, which gives me 0.0975. And so my P2, I need to multiply by both sides by 1 atmosphere, is equal to, move this up a little bit, 0.0975 atmospheres. So to sanity check this, I need to make sure that it makes sense. So when my temperature is at 64.6 degrees Celsius, I have a pressure of 1 atmosphere. When I lower that temperature, I have a pressure much lower than 1 atmosphere. And to me, this makes sense because we know that as we increase the pressure, as we increase the temperature, the pressure should go up because we're giving these molecules more energy to be able to break their intermolecular forces and enter the gas phase. And so it makes sense that as I lower the temperature, that the pressure also lowers. Okay, so this finishes my examples for chapters 6 and chapters 11. I hope this helps interpret the book a little bit and helps you with some of these problems.